Introduction and Principles of Prestressed and Precast Concrete Structures. Presented by Nur Nadia, Sheryna, Syahnur, and Nur Afiqah Izzati. Contents. 1. Concept and Principles of Prestressing. 2. Prestressed Construction Work Procedure. 3. Precast versus conventional and situ construction method. And 4. How precast concrete reduces carbon monoxide and global warming issues. Concept and Principles of Prestressing. Introduction. Prestressing is the process by which a concrete element is compressed, generally by steel wires or strands. Precast elements may be prestressed during the construction process, pre-tensioning, or structures may be stressed once completed, post-tensioning. In the field of civil engineering, prestressing is a method that is frequently used to keep cables taut even under compressive stresses. However, prestressed concrete, in which a prestress force is applied to a concrete member, is by far the most widespread application. Within the field of building structures, most prestressed concrete applications are in the form of simply supported precast floor and roof beams. These are usually factory-made, where the advantages of controlled mass production can be realized. Where large spans are required, in situ prestressed concrete beams are sometimes used, and in situ prestressed concrete flat slab construction is increasingly being employed. In the field of bridge engineering, the introduction of prestressed concrete has aided the construction of long-span concrete bridges. These often comprise precast units, lifted into position and then tensioned against the units already in place, the process being continued until the span is complete. For smaller bridges, the use of simply supported precast prestressed concrete beams has proved an economical form of construction, particularly where there is restricted access beneath the bridge for construction. In pre-tensioning, steel tendons, in the form of wires or strands, are tensioned between end anchorages and the concrete members cast around the tendons. Once the concrete has hardened sufficiently, the end anchorages are released and the prestress force is transferred to the concrete through the bond between the steel and concrete. This method is ideally suited to factory production since large anchorages are required to anchor all the tendons, and several members can be cast along the same set of tendons. In post-tensioning, the prestress force is applied in this case by jacking steel tendons against an already cast concrete member. Nearly all in situ prestressing is carried out using this method. The prestress force in post-tensioned members is usually provided by many individual wires or strands grouped into large tendons and fixed to the same anchorage. The concentrated force applied through the anchorage sets up a complex state of stress within the surrounding concrete, and reinforcement is required around the anchorage to prevent the concrete from splitting. Now, let's watch a short video about the prestressed construction work procedure.
Process starts with engineering. Every product is engineered using the latest design tools, and detailed drawings are created using a 3D computer-aided design process. Once design drawings are approved, they are sent to the factory floor and used to monitor production. Now it's time to assemble the rebar cage. The first step in this process is the cutting and bending of the steel reinforcement. The correct rebar is selected and shaken down off the storage rack, and is then cut and bent to the exact dimensions needed to fit the design requirements. Next, the bars are assembled and tied together to form the reinforcement cage. Rebar wheelchairs are used to help position the cage within the form and to ensure proper clearance of reinforcing. Once the cage assembly is complete, we can begin to prepare and clean the form. Old castle infrastructure uses a variety of steel forms, which are built to last and will maintain exacting tolerances for more than 30 years. At this point, all openings, cutouts, or embedded items are secured to the form. Then a form release is applied to each surface to ensure the final product can be easily lifted from the form. Now that the form is prepared, the overhead crane is used to pick and place the cage onto the core of the form. Care is taken to ensure that the reinforcing cage is stable for transport to the form. Once setup is complete, A certified quality control technician will conduct a pre-pour inspection to ensure conformance with the approved shop drawing. Upon satisfactory completion of this inspection, the technician will sign off and flag the form indicating approval to place concrete. Oldcastle infrastructure uses a variety of certified raw material sources, including cement, coarse aggregates, sand, and chemical admixtures, which are carefully selected and mixed according to the specific design requirements. Each Oldcastle infrastructure precast factory has a concrete laboratory used to conduct routine raw material testing and control exact quantities for each batch. This is especially important when using high-flow self-consolidating concrete. The lab collects sample cylinders used to check compression strength and verify quality of each batch. Once the materials are properly mixed, the self-consolidating concrete undergoes a variety of additional tests, including a spread test to verify the mix has the proper flow and no segregation of the aggregate. The approved batch is transported in a bucket via an overhead crane to the product form on the production floor. Concrete is placed into the form from on location, and care is taken to allow the concrete to float without entrapping air voids. Once the form is filled, the top of the form is screeded off and the specified finish is applied. Once the concrete is placed, the curing process begins. This may include tarping the product overnight in order to capture the heat from the hydration process. The controlled environment of a precast factory enables the product to properly cure and reach the full design strength. Once the QC technician confirms that the product has reached the desired strip strength of 2,500 to 3,000 psi, then the stripping process may begin. This involves opening the outer jacket, collapsing the inner core, attaching the lifting devices, and removing the product from the form. Once the product has been removed, it is then cleaned and the post-pour inspection is conducted. If all design dimensions have been maintained and no visual defects are noted, the QC technician will sign off. The final product is then labeled and transported to the yard. Care is taken to make sure it is stored on proper dunnage as it awaits the customer demand. When the customer is ready to receive the order, the product is loaded on a truck and properly tied down for shipment and delivery to the project site.
Precast versus conventional in situ construction method. Why precast concrete is preferred compared to cast in situ concrete. Precast concrete can be cast into a specific shape at a location other than building site, while cast in situ concrete is cast into forms on the building site. Precast concrete elements are manufactured in a controlled casting environment, which makes it easier to control mix, placement and curing. As a result, weather condition has no effect on the casting work. On the other hand, cast in situ concrete elements are casted on site in the open environment, which makes it difficult to control mix, placement and curing. Thus, weather condition can delay the casting work. The quality of precast concrete can be controlled and maintained easily, while the quality of cast in situ concrete is difficult to control and maintain. In terms of cost, precast concrete is a cheaper form of construction for large structures, although its maintenance cost is higher. On the other hand, cast in situ concrete is a cheaper form of construction for small structures with a much lesser maintenance cost. Precast concrete requires less labors, although requires skilled labors at site, skilled and technical contractor, and heavy machinery and cranes for handling. Cast in situ concrete requires more labors at site, although local contractors can also build the structure, without requiring such handling equipment.
Precast concrete speeds up construction work as it can be installed immediately and there is no waiting for it to gain strength. The increase in strength can be achieved by accelerated curing, and on-site strength test is also not required. High-strength concrete can be used for precast concrete because it is in controlled condition. Cast in situ concrete makes construction slow as gaining of strength requires time. The increase in strength at situ by accelerated curing is a difficult task, and on-site strength test is required. It is difficult to use high-strength concrete for cast in situ concrete as it depends on site condition and resources available. Precast concrete have a much lesser total construction time compared to cast in situ concrete, which makes speedy construction as possible. The construction speed for cast in situ concrete is less as elements are casted at site. How precast concrete construction reduces carbon monoxide and global warming. While a floor concreted on site is made of solid concrete, a hollow core floor with its voids in the core requires only slightly more than half the concrete. This reduced cement consumption is by 1/3 per cubic meter of concrete. Because the precast hollow core slabs are so much lighter, less concrete is also needed for the foundations. Moreover, the number of interior load-bearing walls can be significantly reduced. Carbon monoxide is produced by incomplete combustion of carbon in liquid, solid and gaseous fuels. It can be produced in dangerous amounts when using petrol-powered equipment and gas appliances. Precast concrete allows production in a controlled environment, reuse of formwork which reduce use of equipment, and reduction of waste. Global warming is caused by greenhouse gas emissions that trap the sun's heat. Precast concrete can reduces the need for air conditioning due to its ability to incorporate insulation, hence, reducing production of carbon dioxide. The need to dispose waste is also lessened as less waste is produced and excess material can be recycled. Steel consumption is lower because it is pre-stressed before concreting, and cement compaction is reduced as compaction process in the plant is much more effective. Precast construction reduces use of air conditioning, which is producer of hydrofluorocarbon, reduce the use of electricity and energy equipments which contributes to sulfur hexafluoride, as well reduce aluminium production which contributes to perfluorocarbons. That's all for the video. Thank you for watching.